Okay, welcome to Hong Kong and welcome to BU. It is my honor to give the first tutorial of this exciting event. Um, so I guess many of you already have seen around in our campus, but maybe some of you just feel it's very difficult to find way here. But yeah, that's so today I would like to give a talk on some topics related to this theme of our conference and many related to machine learning. And so it's a crash course of machine learning or deep learning. Uh, in fact, I had talked about this also in BU like 5 years ago. But at that time, uh, machine learning and deep learning, although it is already highly developed, but it's not as hot as today. For example, now maybe all of you use ChatGPT and other tools to just, for example, to help you write your or modify your manuscript. And also at that time, there are not so many like deep fake images or videos. But now I would like to give you some brief introduction on deep learning. And also I would like, because my background is physics, I'm now assistant professor in Department of Physics. So I would like to give you somehow the background. I know many of you also from physics background. So I would like to give you my point of view of how physics interact with machine learning. So our conference, actually the main topics, not only machine learning, but also complex systems. As you may or familiar with some of the complex systems, maybe your research system is a complex system. For example, maybe the complex network such as the airlines, and also maybe you are working with the active matters like bird flocks or the brain, or maybe you are looking to like even in a cell, the metabolic network is still very complex. And even when you are looking into a molecule, the dynamics of a molecule, it's also very hard to resolve. To resolve the difficulties of complex systems, as you may know that in 2021, three scientists won the Nobel Physics Prize, that including Giorgio Parisi. He is like a very famous and very talented uh, scientist in statistical physics, and he developed many uh, important methods in solving problems such as spin glasses. And the other two scientists, they are working in the systems related to the global warming and the climate change. And the Nobel Prize in 2021 was awarded for their groundbreaking contributions to our understanding of complex physical systems, and their background are all physicists. So how can physicists understand complex systems? I would like to show you one example. This is just a simple example. Like we know that there are climate change, or like there are some for example, when a grassland, when it is when it's underexploited, then it's fine. Then there will still be grassland. But when there are so many like sheep, they are eating on this grassland, then the grassland may turn into a desert. So the grassland desert change, it is somehow like a phase transition. And as you are physicists, maybe you can imagine that they are somehow like a phase transition. And actually this is a first order transition. Somehow when it is still in some range, then it may seem that the changes can still comes back. Like for example, if when the system already changed from here, then maybe still it can comes back and still the grassland. But when it reach a critical point, then the grassland will change into the desert, and then it is hard to change from this desert back. So this is somehow very like a magnetic system, hysterias. So to measure or to quantify if this system is around the critical point or is far away from the critical point, one can use some experiment. For example, one can make a perturbation to this system. For example, when the system is highly is very stable grassland, then after some perturbation, it can just return back. For example, if you cut a tree, then that's fine. That maybe a short while later, then there will be some other trees grow up. Then the system returns back. And however, when the system is really close to the critical point, then the changes the perturbations you give to the system will be hard to goes back. And this is somehow the properties related to the physicists that knows very well. Like for example, when the system when there are two states of in a system that originally maybe in one basin, and when the system is very stable, then after the perturbation, the system will take very short time to recover. But when the system is just at the transition point, then at this time it will take a longer time to recover, and you can see there will be high autocorrelation and large variance. And all these features, like for example, recovery time, autocorrelation, variance or screwness, all these can be used as features. And these features can be understood by physicists. And if you learn physics very well, then you can extract these features from complex systems. And these features are signs for our understanding of complex systems. So this is how traditionally people resolve problems in complex systems. But as you may know that nowadays we are not doing things like this, right? Like when after the deep learning paradigm, then the feature extraction, now we don't need some real physicists to do things like to really extract the features from to understand complex system, right? We can just learn from some like configurations of a complex system, and then extract the features by the computer, by the AI, and then based on this AI, and we can do some machine learning tasks, that's classifications. For example, here is an example like car or not a car. And now we don't need some features, but then leads to some problem. For example, previously people can understand the system quite well, then we can interpret why this is a car and why that is not a car. But anyway, your definition can always, you can have your definition for a car, but the real world is much more complex. Maybe car still is fine, but still in the real world, there are some cases that are really subtle and it's hard to give a clear definition. For example, what is a cat? Can you find some real features of a cat from a picture of a cat? We all know what is a cat, but in order to define a cat, then it is really hard. But machine learning can help you that it can extract the features by itself. And we don't need to find a clear definition of what is the real feature or related to a cat, but actually it's much, it seems to be quite easier, but the disadvantages is that it is hard to interpret. And as I know you are all scientists, so maybe you are interested in like how can AI work for sciences. Like for example, a recent review showed that AI can help in doing a lot of things. For example, here it shows that AI like in doing physics, like for example, it can help us to do dimensional reduction. Also, it can help us to like to learn from the corpse, and also it can help us to extract the features and learn the possible dynamics And also it can help us to solve like many difficult problems such as the quantum mechanics, and to help to solve the entanglement in quantum systems. And also maybe you know that the AlphaFold had already be, especially AlphaFold 2 has already become a very important tool for structural biologists, and AlphaFold 2 in the previous CASP competition, it has defeated most of the other method, and had reached accuracy that almost can match the experimental determined structures. So this AlphaFold, it acts as a tool that you can or use this to solve your like biomedical problems. And also, as I mentioned, the OpenGPT can help you to do a lot of things. Like I used it to help me to write emails, and also to write manuscripts, etc. And these are some examples for AI for science, but I would like to give you some more examples that AI and science connected. The first thing is, the first example is related to physics, and it is like how the conformal field theory related to the emergent classical geometry. And you don't need to know about the physics related to it, but I would like to show you something interesting. Is that as physicists, maybe you know that renormalization group, and renormalization is a way to solve that the system related around the critical state, and you can solve the critical exponent with the renormalization group method. And the interesting thing is that also we can use machine learning to do something similar to the renormalization, but the machine learning itself, it was the working of machine learning of, like, for example, I will mention it later, the convolution neural network. The mechanism of this architecture, it was similar to the renormalization group, right? So you can understand like the layer by layer, and extracting first the very detailed features, and then hierarchical features, and then the features at even higher level. And this kind of level by level feature extraction is somehow very similar to the renormalization group. So machine learning and the physics is somehow, the connections are much more deeper. You can use the machine learning to solve the problems such as renormalization group. And also machine learning was doing something really similar to the renormalization group. Also, you can consider an inverse process, that from a renormalized or a coarse-grained figure, and then how can I generate a real configuration of for example, the IC model system? Then you can imagine this is somehow an inverse process, and this inverse process is just somehow a generation process, and that is from a renormalization configuration, from a coarse-grained thing, and to regenerate the original thing. And this is somehow a generation. So these physicists use the machine learning to solve the problems related to this. And also it suggests that the machine learning are just doing something. How machine learning do normalization, how the machine learning do the generation, it's somehow very similar to a physics process. And another example is my work, and I'm using the AlphaFold to extract, to compare. I'm using the AlphaFold predictive structures to compare the proteins in different organisms. For example, the proteins in E. coli and the proteins in human. What are they different? So I selected those proteins with similar chain lengths, but as you can see in the figure, that the figure shows the radius of gyration, and you can see that although these proteins have similar chain lengths, but their radius of gyration diverge. For those, for example, E. coli, and they have smaller radius of gyration, but for like C. elegans or human or mouse, it has larger, much greater radius of gyration. And it seems that the organism complexity is correlated with the radius of gyration, somehow like this. Why would this happen? And when I look closely to the dynamics of these proteins, and I find out that these proteins, when their shape are changing, you can imagine that when the protein evolves from a densely packed like sphere-like structure, and then it evolves, and when it has more modules and the two modules connected with a very flexible chain, and in this way, this protein will become a two-module structure, and this protein will have a larger radius of gyration, and in this way, this protein can behave is like a inter-module dynamics. For example, originally when the protein is densely packed, it cannot perform like large conformational changes. But when this protein can have a very can be divided into two modules, and then this protein, you can imagine that it can has this kind of module inter motion, and when they are more significant modularized structure, then it will have more significant this kind of low dimensional motions, and this is how the I think how the statistical trend in protein evolution, and actually this kind of evolution is somehow also similar to the machine learning thing. Why? Because when the protein evolves and its specific function was selected out, it's somehow very similar to as you train a machine learning system, and then finally this system can perform some specific task. And when the more you are working on one task, then you are becoming more specific on that specific task. Originally, maybe after some really pre-trained thing, and maybe your model is still somehow capable to solve not only one task, maybe you can solve the task like some different task. But when you are really trained or evolved towards the capability of solving one task, then some direction, some will be selected out. And then this will lead to somehow we call the evolutionary dimensional reduction. And this is somehow very similar to the machine learning. And when it learns specific tasks and it generalizes with it, and then it can become very specific in solving one task, but then it lost the capability of solving some other task. And also, not only like to research like this, but also, for example, in this meeting, you will meet like Professor Tu Yihai, and he used physics to solve the problems of the stochastic gradient descent. And some of you yesterday also joined the seminar by Professor Gong Plin 老师, and his talk mentioned that the stochastic gradient descent may be not that important, but the multi-fractional fractal structure of the landscape also works for in helping the system to find the flat minimum, and also it can always helps the energy minimi process. And yeah, so stochastic, I will mention stochastic gradient descent later. And also there are many other mappings between science problems and also machine learning problems. For example, some people think that the residual network with skip layers is somehow can be mapped into a like solving ordinary differential equation, the ODEs. And also there are some people think that the landscape in training the machine learning systems is related to spin glasses, or even the landscape is similar to protein folding or something like that. And these are all the connections between AI and science. What I want to show here is that AI and science, these two topics, is somehow really highly correlated. You should not think that only AI can be applied to solve scientific problems, or AI is just tools. But I think the most interesting thing is that your point of view in science can also help to understand AI, why AI can work, and also can help to develop AI and to help us not only in solving problems, important problems in sciences, but also helping us to solve problems in AI. And since today is a tutorial, I would like to recommend you learning material. That is this Dive into Deep Learning. This is an online book, and you can find that all the examples that you can find code. So you can easily implement all the algorithms related to this. But since time is really limited, I will just really quickly go through some basic the outlines of this machine learning. So I had just talked about some like the connections between AI and science, and then as you all know that, so this slide was something that I prepared at the few years ago, and this was copied from some other lectures. But you can see that at that time, I find there's some very important applications such as image classification, speech recognition, and also the auto cars, and also in biomedical use. But nowadays we can see that there are some more applications such as ChatGPT. And in machine learning, there are some very simple tasks, and I think maybe you are all very familiar with, so I will go through this part very fast. And first, maybe you can think about there are two concepts that seems to be very similar, but they are different. First is classification and clustering. They are different. So clustering is an unsupervised learning. So when you are doing clustering, you don't know which data is belonging to which class, right? You are just clustering those data points that looks similar. So this is clustering. But for the classification, you will know that which data is. So yeah, classification, like this, like somehow a supervised learning problem. You already know which data is which. And so your task is to find like a boundary line that can helps you to divide those data from one group and to another. So this is supervised learning, and this is classification. So, and for the unsupervised learning, like for example, clustering, you can also use some unsupervised way to do the dimensional reduction. That is, as I had mentioned, you can use when you have the data, you want to see that what is the principal component, what is the basic trend of this data, and then you will do the PCA. And I guess many of you have tried to do something like this. And this PCA is somehow unsupervised. And you can also find a supervised way of dimensional reduction. For example, here is I showed example that the linear discriminant analysis, this LDA. So as you can see that if you are doing PCA, then you would like to find where can I? You would like to find the basic trend of this data. For example, this left-hand side, that the data was extended along this direction, up direction. But actually, this direction, although it is the data, how the data lies, but it is not the direction related to the correct way to distinguish these two class of data. So in order to find the discriminant line to make these two groups of data apart, you need to find as a right-hand side, as it shows, that you would like to find the direction that can make the two groups of data that are far away from each other. So this is when you know the answer or you don't know the answer. So this is the LDA. And also, in order to solve this problem, you maybe not only dimensional reduction, maybe sometimes you first need to raise up the dimensionality of this system. For example, sometimes the problem on the low dimensional space is hard to distinguish the data from one to another, but when you raise up the dimension, then it's okay. And here are some examples of, like, for example, the figure at left-hand side is like to help understand how can you determine the boundary of two class. Although you can find one very zigzag boundary, but that boundary also can help you to distinguish the two groups, the cats and dogs. But although it can, for the training set, it can make the two groups of data that works very well. But this line are too complex, and it may overfit, right? So this is not a good line. So sometimes maybe we need a simpler line, and to do as you may know that the classification, there are some other problem. Like for example, if is one line enough, or I need more lines, and some problems they are linearly non-separable. So I give an example of exclusive OR. And also to do the classification, we have many different methods. Like you can do the logistic regression, naive Bayes, and like SVM support vector machine. And I showed a little bit. And also there are some problems, as I mentioned, it needs the nonlinear problem. So for example, left-hand side is an example that some data are inside, they are a group, and outside there is another group. In order to make them into two groups, it is hard to find a line to cut them. But if I make all the data to like to multiply them with like a radius, then the data can be separated in and with one plane. And also another problem is that sometimes in the machine learning we need to, for example, here the example you can see that these two are one person, these two are one person, but when you are doing you are calculating the distance between the figures, then you will find that these two figures are more similar, but these two figures are more similar. But you don't want that, right? You want to distinguish who is who. And in this case, that the distance between the two things may be not usable. And in that case, why it's not usable? Because maybe sometimes because this manifold is too complex. And on this, the Euclidean distance between these two data points, they are short, but actually they are not connected. The real distance should goes along this manifold. So in order to get a correct distance between the two the figures, you need to collect the data, for example, from the front of view and then slightly change, and you need to collect a lot of data points. And with all these data points, and then you define the distance, not by the Euclidean distance, but like connecting those neighboring points, like and you first generate a lot of configurations, and then the distance are determined by maybe, for example, the Floyd algorithms, and they are first only connecting those neighboring data points, and then based on this, then you can get the real distance. And this kind of distance in physics is called the geodesic distance, the 测地线. And so that is how you should define the distance. So this method is called the manifold learning, and there are a lot of manifold learning algorithms. For example, here is the isomer. I remember a few weeks ago we also discussed about this in our group meeting. And the history, I think you all know something that the like neural networks, they are developed very early, but only after the 2006, and the neural network, the artificial neural network revived, and then many people start to consider of this deep learning. So deep learning, like it has many layers, and it can help us to extract features at not only one level but many higher level things. So in deep learning, I think there are many things are important. So I listed 4 things I think are important. First is the data. So the deep learning highly rely on data, and also the learning strategy is also very important. For example, sometimes you're doing reinforcement learning. What is your learning strategy? And also architecture. And then like for example, here I showed a long short-term memory network. Like it can be applied in solving many problems. That if you find an architecture that are really suitable for the data, then maybe sometimes you can solve the problem quite easy. But sometimes you can use some method that was not developed for this, but then you can use that architecture and to find some new interesting things. And also the last thing is, I think, most interesting for physicists is the tricks in deep learning. For example, as I mentioned, the stochastic gradient descent. So the stochastic gradient descent is somehow like training method, but also it's like tricks. But it has very deep physical meaning. And also here I showed dropout. Dropout is somehow like when you are training, so So it's here. When you're training a neural network, but sometimes some of the perceptrons, their information will be dropped out. So you can understand it in many different ways. So when this data or this information are somehow dropped out, you can understand it that because they are randomly dropped out, so somehow you are not only training one single neural network. Actually, you are training an ensemble of neural networks, right? So one way to understand this is that by doing this dropout, you are actually not training one single neural network, but you are training an ensemble neural network. This is one way of understanding it. And the other way to understand it is that, as I mentioned, that when you are using too much parameter to fit it, then you will overfit. But when they are doing this dropout, there are sometimes some parameters, they are not important. So this method can help you to avoid overfit, right? So the tricks you can for physicists, you can understand these tricks and with some physical meaning. And in this way, I think that is really interesting. And I think many tricks of deep learning that can be understood by physical analysis. So then I guess you maybe already know something related to the basic artificial neural network. So this is an example of a very simple perceptron. So these X are somehow input, and the first there's a 1. The 1 is a bias, and then when they are linearly in the product with the weights, and then we get the weighted sum, and then with a for example step function or like sigmoid function, or maybe you know the ReLU function, and then to activate the when it reach threshold, then this neuron will be activated. So this is the illustration of a perceptron, and this is something like to plot it in a like this, and then this is one layer and one perceptron, and there are multiple perceptron and multiple layers, and this will gives you a deep learning, the basic framework of deep learning, and how to train these deep neural networks. And maybe you already know that we can use the back propagation to train the neural network, and the back propagation is actually the chain rule. So here show the example that so first they are so originally from the input, then get the linear thing, and with the activation function, it becomes nonlinear, and then the second layer nonlinear, and third layer nonlinear, and then finally get the thing. And when you are calculating the gradient, then it is somehow like the first it's like this. So first this one, and times this one, and times this one, times this one. Yeah, like this. So this is back propagation, and this actually the chain rule of just basic calculus. And I had shown that the previous slide showed that the simplest neural network is just a deep neural network, the simplest case. And actually there are many different architecture of neural networks, and and you can find this kind of neural network galleries from the internet. There are a lot of things, but today I would like to give just very few examples of this. So first, I think maybe you should know is the recurrent neural network. So recurrent neural network that looks not like a deep neural network, but actually it is a deep neural network. So it is like because it's recurrent, so you can see something that is always recurrent inside just seems like a module, but actually you can unfold it into like the different time steps. Like for example, the first t minus 1, xt, and t plus 1. And then in this way, you can unfold it recurrent into multiple layers. And in this way, you can see the connections between the recurrent neural network and the deep neural network. So you can understand why that we say that the RN is a kind of another shape of a deep neural network. And there are many different kinds of recurrent neural network. For example, one input and one output, or one input, many output, or many input, one output, and different kinds. And RN can be used to solve many different kinds of problems. For example, speech recognition, and from the speech, and you can get the output. So this is like input is a sequence, output is a sequence. So this is somehow also called a sequence to sequence. Also, it can be used to generate things, and like generating this music, or yeah, and there are many different tasks. And also, like for example, maybe you are be interested in this, like it can be used in bioinformatic tasks, and you can use this to find some important, for example, some important targets that can bind with some proteins or something like that. Yeah. And these are some applications of RN. And the interesting part is what is the input of this RNN? So usually in like for example, a natural language processing task, you are dealing with words. But actually words, there are many, many words, right? That in a dictionary, you will see like thousands or tens of thousands of words. And how can we use the mathematical way to describe one word or something like that? So we need some method to encode all the words. So one naive way to encode words is like we make every different word into one dimension. Then no matter how many words inside in a dictionary, then you will need the how large the dimensionality of a vector. But that is not a so this way of encoding words is called one-hot way. But this one-hot way of encoding words is not a good idea, right? It needs a too large space to store the coding of the words. So we need to reduce the dimensionality of the words. So this kind of method is called word-to-vector, and usually word-to-vector will be used in all the language processing tasks. So it helps to reduce the dimensionality of words. So for example, if we use all the words, if we use one-hot coding, then the dimensionality will be really large. But when all the words, the dimensionality will reduced into a few dimension, then like for example, here maybe like tens of dimensions, then the dimensionality of the words can be reduced. And also we can find some interesting thing. Like for example, there are some relations. For example, the queen minus king equals to woman minus man, right? This is in this vector space. You can find some interesting observations, and also you can find many, even some sociologists, they would like to use this to understand how the meaning of words evolve in history. So, for example, that the word gay, its meaning changed, and maybe dozens of years ago, the word gay means happy person, but nowadays we don't use this meaning. So if you can use this to, if you find their encoding vector, this reduced dimension word to vector, and you can find the meaning of this word change and evolves in the space. And here now, for example, you calculate the king minus man plus woman, and you will find this vector is somehow parallel with the vector queen. So in this way, we can not only reduce the dimensionality of words, but also it is a really good way, and all the input of the like a sentence or something, they are all using this word to vector method. And another thing, so the recurrent neural network, you can be used in like dealing with natural language processing process. And another is the convolutional neural network, the CNN, that was usually used in like computer vision task, like for example, to understand the handwriting or to understand the face, to do the classification of face, and also you can be applied to analyze for example, the graph or the molecules, right? The convolutional neural network. So as you can see from so first it's stacked with many layers, and also there is a convolution. So what is the convolution? So here are some examples. So originally this the 3x3 matrix is the original figure, and the 2x2 is a convolutional kernel. You can understand it like this. And then after this convolution, this original 3x3 matrix will be made into a 4x4. but not 2 by 2 matrix, and you can see that is somehow the calculation is easy. That the original data and the product with the corresponding entries inside the convolutional kernel, and by this you can get convolution, the result for convolution. So this convolution calculation is very similar to a coarse-graining of original figure, right? And you can use multiple channel of a picture like RGB or some multiple channel of a figure, and also you can use multiple convolutional kernels. And then with all this information, and the convolutional neural network just extract this information and from the original figure. And then you can see this convolution are doing something like it's extracting the information, but not only those information, but also the information with the neighboring ones. So it's a coarse-grained representation for the data. And also recently, maybe you all know that there is another way for extracting the information, that is the attention. Attention is different from convolution. So convolution, as I mentioned here, all the calculations, they are only related to the neighboring thing, but the attention, somehow it can relate to not only the closest neighbor, but also some non-neighboring ones. For example, here is an example. She is eating a green apple. So you can see that neighboring, like for example, eating and green, they are somehow close to each other. But eating green, they are not so correlated. These two are not so correlated. The correlating thing is that the eating and apple, these are correlated things. So when you are doing a natural language processing task, you need to, when you are reading eating, then you need to find what is she eating. So your attention will be at the apple, right? Not the green. The green is not so important. And you can and then how can machine learning not to find the neighboring one to do something like the convolution thing? That is how the attention will do. Attention will be trained that can helps you to find like the correlations, not only the neighboring ones, but also there are some long range ones. And maybe you all knew that there was a paper called "Attention is All You Need." That is in that paper that it was the transformer was established, and this kind of things that has really be a really pioneering work. So that after that there will be BERT and also GPT, etc. So that's why nowadays that the language task the machines are doing so well. And with the attention, then there will be transformer. And as you may know that AlphaFold, as it can predict the protein structure, AlphaFold also use the attention and also use the transformer. And in the AlphaFold, inside AlphaFold, it's called the evoformer, right? Because it uses evolutionary information. And attention can not only be applied in doing like language processing tasks, but also nowadays the attention can be used in the computer vision task. And here then you can see somehow when you are looking into this picture, and your attention will be only focused on how this cat looks like, but not the background thing. So this is how the attention can be applied in CNN. And then I had talked about the RNN and CNN. Another thing is the autoencoder. Maybe some of you already used this in your scientific research. The autoencoder is the basic thing is like this. It's a neural network, and it gives you an input, and it needs to give you an output. But the output, you want it to become the same as the input. Okay, but when output is the same as the input, it seems to be meaningless. But why it's useful? Because the network architecture. So the input is really high dimensional, but then the encoder becomes smaller and smaller, and then it reaches a bottleneck. And then on the other side, from this bottleneck, and then this get larger and larger, and encode the decoder, so that the input and output can become the same. But please pay attention that in between there is a bottleneck there, and this bottleneck has very few numbers of neurons. And if, for example, here the input and output can become exactly the same, it means that in the bottleneck layer, that with only very few neurons, it can already extract the key features of the original input. So we can use this information, that is a nonlinear dimensional reduction of the original figure, right? And with the autoencoder, and you can also change it and make it into a generative model. For example, this is called a variational autoencoder, the VAE. So it's very similar to the original autoencoder, but then in the hidden layers, the bottleneck part, it's not just to reproduce the original input, but it tries to give not only the it tries to give a latent distribution of the original inputs. Like that, for example, when it's Gaussian, then it will give you the mean value and the covariance of the original data. And based on this extracted key feature, for example, here is a Gaussian distribution, then I can resample things from this Gaussian distribution and put it into this bottleneck layer. And then the decoder will generate a lot of things. That is not exactly the same as the original input, but somehow it obeys a similar distribution as the original input. So when it learns from the original input, then it can generate something that is very similar to the things from the original data set, but somehow it's a little bit different from that. So this is a very simple generative model. And after that, the people find that generative model are really useful. We need to use it to generate not only the handwriting numbers, but also to generate the face, music, and also maybe videos. And in that case, that a few years ago, there was a very, the generative adversarial network, the GAN or GAN, becomes a very hot topic. So the GAN is like this. So it's training a generative model, a generator, but at the same time, it's training another network that's called a discriminator. So when you can generate a picture that is really like the training set, but your discriminator can easily find out that this is not that this figure is fake, right? Then you need to improve your generator. And then when your generator is becoming very strong and the discriminator cannot distinguish whether this picture is fake or is from the training set, then this time the discriminator is good. Then you need to improve your generator. And by this kind of minimax objective function, by this kind of training, you will have a very strong generator and also a very strong discriminator. And in this way, you can generate like the figures that is really very similar to the that looks really real. But nowadays, the generative model still very hot, but the GAN is not as hot as a few years ago. So nowadays we are using the diffusion model to generate pictures. Like for example, maybe you use this kind of apps and you can write something describing this figure, and then you can use the cell phone app to generate a picture. That is, and how would this do? So it is somehow using a totally different ways of generation. Like the previous, I showed for example, the variational generator, you need to learn how the original data is, but here it's not like that. So originally when you have a figure, a picture like this handwriting E or something like a spiral line, and then you can use some diffusion so that makes this E to become more and more first blurred and then diffusion so that you can get a noise, a random noise. And then when your model can learn this, not only the forward trajectory, but you can do the reverse, that then it means that you can use this random noise to generate a figure that looks really likes the original ones. Then what you need to learn is the drifting terms. And if you learn the correct drifting, and this drifting is related to how you describe this figure, right? And then you can generate the figure. So this is called the diffusion model. Well, what I think this diffusion model, like somehow very similar to like maybe like Waddington landscape or something like that. That originally maybe it's like the stem cell, and it can be developed into different cell types. Yeah, so that's what I'm thinking of. Okay, then I had talked about the different architecture and different ways of and many hot topics in machine learning. And in the last part, I would like to give you some very important concept in machine learning. First is model capacity, like when you are fitting the data like with only a few data, the data is there, but you are fitting this data with a few parameters or many parameters, right? You can, for example, there are like 5 data, and you can fit the 5 data with 5 parameters, right? And there is an old saying, the von Neumann said that with 4 parameters, you can fit an elephant. So there is a paper called How to Use 4 Parameters to Fit an Elephant. So yeah, you use 4 parameters, you can fit elephant, but people will think that when you are having more parameters like this, then or more complex function, then you will have more chance to overfit. And when you are doing this, so this is about the overfit thing. And in the training, maybe you also know that with the training data, like after the training error will always go down there. But when you have some new data, like the testing data, then you will find that if your model overfit, then somehow there will increasing variance. So it fits well with the training data, but it cannot fit the testing data, right? And so this is the traditional way of understanding the neural network. But it's somehow, the real world is always more complex than what we think. And the deep learning, so first maybe I should show you this. So that is somehow traditional ways of understanding machine learning or neural network. But recent years, people are more and more finding that with a large model, we can still fit, we can still get so I had just talked about this under-parameterized regime, that when your model is becoming more complex or after your training, then originally this error should increase, right? Because you overfit the model. But nowadays people find that with a larger model, even larger model, more complex model, then the error will still goes down. So this kind of phenomenon is called double descent. So the first regime is here and another regime is here. So it means that with a very large model, like for example, nowadays the GPT, their models have large numbers of parameters, but it can still works quite well. So that is because they are going into this regime, so that the errors can still decrease. So this is, I think, this is the most important thing and the most interesting thing in machine learning. That is in deep learning. That is, deep learning can fit things that is easy to understand, because when you are having a lot of parameters, you can do everything you want to fit. But the interesting thing is that with this kind of large model, you can still fit correctly and you will not overfit. That is, I think, the very interesting thing. Why with large numbers of parameters, but you still can fit, or you can still get really low error and you can fit it correctly. That's somehow related to problems that I think is, like as Einstein said, that the most incomprehensible thing is about the world that is comprehensible. So I think that maybe I should give you some examples. So when you are looking at this random noise, you cannot understand anything of this. But in order to get information from this figure, or you want to memorize this figure, then you need to, it's a really hard problem, right? And you cannot distinguish with this random image and another random image. It's hard for you to do that. But for natural images, then you can see that these figures are much easier to understand. But still these data are high dimensional. Although these data are high dimensional, but they are somehow easier to understand. Why? There are many reasons. Like, for example, from here, that the numbers, for example, if I hide the bottom half of this figure and ask you what is this number, and you can imagine that this number is 1, with only the upper half, the top half of this figure, you can guess what is the bottom half. And for other things, you can also, for example, here 9, I hide the bottom half. Maybe you will guess it's 9, but maybe you will also guess it's 8. But no matter what you guess, your guess is almost there, that you have a half probability of guessing the correct answer. So it means that although this data still maybe this having same pixels as this random image, but originally this data has many correlations inside this picture, so that actually this dimensionality of this figure is much, much lower than these random images. So that's why we can understand things. We cannot understand high dimensional things, and but we can understand these natural images, because this natural, for example, this car is symmetric. So we can understand physical laws because there are many symmetries in our physical world, and there are some locality. Like, for example, we can get the pixel, we can infer the pixel with only the local information, and we can get that. So this is somehow, but from these random images, it's hard for us to guess a pixel from its neighboring ones because it's totally random. Therefore, our brain are somehow evolved to become very simply can extract the low dimensionality of the real world thing, not the random thing. And also the interesting thing is that the machine learning also although with a very large model, just similar to our brain, but it can still, with, for example, this double descent, it can still extract the low dimensional features or of the real world thing. So it's somehow, this is really interesting thing, and I don't think this problem has been solved. So why would this low dimension, the deep learning also can helps to find a low dimensional or that the solution of this? And yeah, so I think this is an interesting thing. And then in training, maybe you will ask, sometimes the loss function are important. For example, I had mentioned a little bit, for example, in the autoencoder, I mentioned that the training was, the loss function was to minimize the difference between the input and output, right? And also regularization is an important trick in machine learning, that we want to fit we want to learn to fit the data, but also we want to fit it with a smaller model, that model with lower capacity, or we want to use fewer parameters to fit the model. So then we will need the regularization term that maybe it's there are different ways of doing regularization. For example, the total weight, the summation of total weight or total number of the parameters, then we can use different regularizations. And also, like in the training of the neural network, we need to set up some hyperparameters that how to, like for example, the learning rate, and also, as I mentioned, the regularization constant. Also, in your in the architecture, maybe number of hidden layers and the width of the neural network, the nodes in each hidden layers, etc. And when you find the correct number of so this process that in finding the proper hyperparameters in machine learning, that in Chinese, that maybe many people say this is 炼丹, and to find the best hyperparameters so that you can fit you can do the machine learning, right? And also, as I mentioned in the very beginning, I said that I mentioned the stochastic gradient descent. This is also a very important trick in doing machine learning. So originally, when you are calculating the gradient, so this is the total loss, and this is the loss from each data point. So this is the loss. And in order to calculate the gradient, you need to use this loss to calculate the gradient. But this M is the total number of real data. But in stochastic gradient descent, it's not doing this kind of gradient calculation. It looks quite similar, but here this m becomes the m prime. The m prime is the number of the data points in a batch, right? So it's not the whole data set, it's randomly sampled from the data. So this is easier to calculate. But the more important thing is that this is not only good for calculation, but also it helps you to generalize well. So that is, I think, is very important thing that you need to be careful, and you will listen to many talks related to these topics during this conference. And the interesting thing that when you are randomly sample data from the original data and calculate this gradient, somehow you are not, so this kind of noise is not a thermal noise, like just like a random thing, but this noise is related to your data, so that it will have some features inside the data. Actually, it's like you can prove that this noise, the covariance of this noise is proportional to the local feature information of this loss landscape, so that there will be, as Professor Tui had mentioned, there will be the inverse variance flatness relation in SGD, so that inside the sharp minimum, somehow like the temperature is high, and in a flat minimum, the temperature will be low. And the interesting thing is that the flat minimums are good in machine learning tasks, because in a flat minimum, like when you are having a testing data, so the training data and testing data is somehow like this black line and the red dashed line. The red dashed line is somehow with the testing data. Like the testing data is not exactly with the original training data, but it's somehow a little bit different from the original one. But when it is at the flat minimum, then you can find that with the testing data, still the loss is quite small. So that it means that when you are finding, although the loss of this flat minimum or sharp minimum are the same, but inside the flat minimum, it can deal with more new testing data, so that it can generalize much better. And the stochastic gradient descent prefers flat minimum. So it means that when you are training the neural network with the stochastic gradient descent, you will always find an answer that is not only having a very low loss, but also it can help you to generalize well. And also, as I had mentioned at the very beginning, I mentioned dropout. It's another way of it's a way to doing regularization, and also it's another way you can understand it as an ensemble learning, so that it can also helps you to generalize better. And there will be more tricks in the machine learning things. For example, you can add some data augmentation. Like for example, when you have a data set of images, you should also do, like for example, make the images to rotate with an angle, or to flip the images, or etc. And then there are many other tricks in the machine learning. And for example, also to avoid the overfit, you should also you can also use for example, the early stopping, that you don't want. As I mentioned in my research, that I had shown you that the proteins are evolved towards a specific function. But if you early stopped, then this will not be so that overfit, right? And deep learning can solve a lot of things, but it can also have some problems. So here I would like to give you two examples. One example is that for example, this is a panda, then we all see this is a panda. But sometimes in machines, that when it was attacked, this image was attacked with a little bit noise, then somehow the machine will not give you the correct classification of the image. So this kind of thing is called adversarial attack. So this is somehow related to how the machine, the generalization problem of machine. So it is something like when you are fitting the data with a very simple model, then it is easy for you to perturb. For example, if you find a boundary line, and then I can just find a data point just close to that line, but it's orthogonal to that direction. Something you can find So this is when your model is easy, then you will be easy to get to be adversarial attack will happen. But if you fit the model with a very complex model, then it will be hard to find, maybe it will be hard to find this adversarial attack, but then your model will be too complicated and maybe cannot generalize very well, right? So this is an interesting thing, and I think physicists maybe can help in solving problems like this. Another topic is the catastrophe forgetting. Like this is related to called multitask learning or transfer learning. When you are after your training with one task, then sometimes you will need to learn another task, but you don't want the system to forget the first task. Then in that way, you would like the system to go in this line, because in this line, these two ellipsoid means the laws are small for task A and task B. And you go this line or you go this, you go this two line, then this one is you forget both A and you have not learned very well with task B. And this one, you learn task B, but you forget about task A. But this one is, you can remember both, work well with task A and task B. But sometimes, for example, in my another research, I would like to find somehow a direction like this, because I want the system to get far away from the original one and to fast go to another another task. For example, from the resting state to the task state, the brain will reconfigure, and somehow we need the task state to be really distinguished from the original resting state. So maybe we need to find some direction that is not like this. But anyway, physicists can also help in solving problems like catastrophe forgetting. Like, for example, which connections are important in task A and which connections are important in task B. And I know that many of you, like for example, the students attending this summer research program, we had discussed many times on the facial information thing, and you can find that each bond that was it how large is this facial information related to task A, and we use that as a constraint, and this is called elastic weight consolidation, EWC. And there are many challenges in deep learning, and since time's already there, so I will not give very detailed introduction. But anyway, I think I had mentioned about these things in the discussions, and that's all. Thank you. Yeah, please feel free to ask questions, or that's all for my. Yeah. Please. Yeah, you can ask questions, or just if you want to go to the bathroom, or if you want to buy breakfast, or if you want to go down there to see what they are doing, then please feel free to move. Yeah. Or if you want to have some discussion, please feel free to ask. And那个新闻，你帮等一下，如果有人提问，你拍照啊，或者是yeah, okay, yeah. If you have any question, please feel free to ask. That is you should learn. So it's learning by learning how it diffuse from by learning this forward trajectory, and try to learn the reverse one. Yeah, sure. They may be different. So that's why you need the description of this figure. It learns like, so that's why I think it's like a Waddington landscape or something like that. It's like this the description of this figure is somehow guides how it will evolve the drifting terms of this from the noise. Maybe it's somehow, but there are no that adversarial like network. So yeah. Oh,
How it, I want to ask what is latent space and how it helps in the diffusion model.
what is the latent space? I'm not so, I'm not an expert in doing this because I just use this and the I think we should yeah the here the latent space is like I'm not sure in here I'm not showing the latent space of this yeah I'm just in here I just want to show how this diffusion works. I'm showing that how the real training process how it happens. Yeah. So I just want to give gives you just intuitive understanding for this diffusion model. But yeah, if you would like to know more, I would suggest you to read some more references. And I'm not an expert in this. Yeah.
Okay, thank you.
But anyway, that recently that I know that many people use this diffusion model to generate, like uh, for example, in all kind of things, like to generate the possible configurations of in the proton dynamics, or to generate like the possible uh, the like the interacting patterns between uh, one molecule with another, and they can all use diffusion model to do that. Not only be applied in generating pictures, but anyway, that now the most important thing is that we use this diffusion model to generate pictures, and it defeats the previous gun. And, yeah. Yeah.
Thank you. I just want to know, we have different type of data, such as sound or image, and any different data from the reality. How can we select a suitable network according to this status? Yeah, just make a comment.
Okay, this is not a simple question, and so in my understanding, so you should know that usually what will one people use this data to, like for example image, then people will usually use the CNN to do the learning. With the time series, people will use the RN to do the learning. So first you should know this, and then after you knowing this, then you should try to use for example, then when I'm learning a network, learning the graph. So if I want to use to learn the graph with a RN, then maybe I can do some random walk on the graph, and then I can generate sequences, and I can use these sequences and to learn these sequences with the RN. So this I makes the graph into sequence, and sequence can be solved by RN. So this is one way of solving it. Another thing is that we can also learn the graph with the convolutions, right? Then I can also do, like for example, then in the convolution neural network of images, then these convolutions are based on the neighboring pixels. But then you can also change this into the neighboring, like the nodes. You can do the convolutions on the network. Then we will get the graph convolution network. So I think the important thing is like how you when you are familiar with one thing, then you can use it, and maybe sometimes you can then it can work, and then this is quite flexible, like to learn something. But if you want to extract something very important, then maybe something will be, for example, as I mentioned, that random walk can help you generate sequences, and you can use that to, for example, you can do that to, as I mentioned, the word to vector, and also you may know that there are some node to vector or some deep walk. Then by making this the random walks on the network into, but maybe here there are some constraints that are related to this. For example, the network topology and how because the language, we know that there are some Z floor and there are power laws inside there. And when you are working on a network that does not have any power law thing, like for example, you're on a random network or in maybe a small world network or something like that, maybe it is not suitable because this random walk, they will not have the scale-free behavior. Then maybe it is not suitable for you to use this random walk on a network and then and maybe this is not a good idea to do this. And I think this is closely, I will not give exact answer for what to use, but it really depends on many different things. So with data, then you can try to mix it into different ways of, for example, and as you may familiar with the time series, and for a time series, you can use Rn to do that, but also you can use that, for example, make time series like xt plus 1, xt plus 2, and all this into like a figure-like thing, and you can use that to do the dimension reduction. It's still possible. So I think there are many different ways, but you need to be careful that not all the ways of transforming the original data into another familiar type will work, because something may be still quite important inside there. Yeah.
Thank you.
Yeah.
As for the double descent phenomena, it looks pretty much like a phase transition process. So do we have any clue of what toy models that could be ready to apply to explain this sort of phenomena? Do we have any clue?
For what kind of?
For explaining the double descent phenomena.
I'm not sure what will be how
okay.
could we? Yeah, there are many theories related to discussing of this. Maybe some saying that there will be a phase transition there, or there may be something. But I don't think this problem.
Must be some phase transition, but
yeah.
Do we have any clue of what sort of like non-toy models that could be ready to explain?
Yeah, I guess that in this meeting that there will be some people talk about this topic. Like I guess that Dr. Tailing Wu, and he will talk about something related to this. But yeah, I think that maybe I'm not sure. I guess there will be some signs that, for example, you will observe that some power loss in this in the double descent region, but I'm not so sure what what exactly. And there are some different models in understanding this. And for example, as I know that there are some guys using, like for example, neural tangent kernels or something to understand this. Yeah, but anyway, like I think this kind of problem are not. Although you may find an answer, but maybe someone will find another way of interpreting this. But this kind of problem is in my understanding, is just like leads you to find some more models or to find some more data to prove the understanding. But it is hard for you to find the exact answer for that. It's something like that.
Maybe I could ask a minor question about this.
Yeah.
According to the current data, do we know the exact point of the transition, like through the computations, etc.? Do we know the exact point of like what we must have some parameterization of the complexity of the system. So at which point of the parameter we use to parameterize the complexity? Do we know the exact point of the transition? No. Yes.
For me, I don't know yet,
Okay.
but I guess it's I cannot answer this question yet, but I guess this is an interesting question, and maybe we should do some, like, for example, finite size scaling for data in different sizes, and maybe we can find out how this this transition will scale with the data size. Yeah, and in that sense, maybe we can find answer of that. And I'm happy that you can ask these kind of questions, and I think this thing is somehow doable. But basically, we need to first set up some basic setups and then use data in different sizes, and then maybe we can do something like that. Yeah, and yeah, if there are no question, then I think we should end here then, so we can still have some time to have rest, because the Professor Joe already come. Then yeah, the next yeah, that's all for my talk, and thank you very much for your questions. And yeah.